Welcome back to the deep dive. Today, we are going to try and move a mountain, or maybe more accurately, we're going to try and move the birthday of a mountain.
That is a heavy lift. We're talking the age of the Earth.
Right, and this is one of those topics where the cement feels, very dry. You go to a museum, you open a textbook, you watch pretty much any documentary, and you're given a number.
4.54 billion years.
Exactly. It's not presented as a guess. It's stated with the same confidence as, like, gravity.
It has to be. That
What?
number is the foundational timeline for all of modern geology and biology. Without those billions of years, the whole standard model of evolution it runs at a runway.
It needs the time. But today we're looking at research from a Dr. Jim Mason. And I want to set the stage here because this isn't just some guy with a bone to pick.
Yeah, his background is pretty serious.
He's got a PhD in experimental nuclear physics, former VP of engineering in the defense industry. And the really interesting part is that for most of his career, he was completely on board with the evolutionary timeline.
He was. He became a biblical creationist later in life. But even then, he said he held on to the old Earth's view. I mean, as a physicist, the math behind radiometric dating just seemed irrefutable to him.
Just hard science.
Right, until he actually looked under the hood.
And now he calls it the sixth Achilles heel of Darwinian evolution. His whole argument is basically that the physics of decay is solid, but the history we apply to that physics is, well, let's call it imaginative.
That's a very polite way to put it. He says we're measuring something very precisely, atoms decaying, but we're interpreting it based on three huge assumptions we just can't verify.
So that's our mission today. We're going to take apart the clock. We'll look at how this dating actually works, those three assumptions that might be breaking the whole system. And then this is the part I found most shocking. What happens when they test rocks where we actually know the age?
The blind taste test of geology. That's where the rubber really meets the road.
Okay, so let's start with the mechanics. I pick up a rock. It doesn't have a born-on date stamped on the bottom. How do scientists get to 4.5 billion years? What is actually happening inside that stone?
It all comes down to instability.
Mm-hmm.
Certain elements, like uranium, are unstable. They're radioactive.
Okay.
And over time, they just naturally break down. They decay into a stable element, in this case, lead.
So uranium is the starting point and lead is the finish line.
Yep, the technical jargon is parent for the unstable one and daughter for the stable one. And the key is this change happens at a very, very predictable rate. We call it the half-life.
And that's the time it takes for exactly half of the parent atoms to become daughter atoms.
Exactly. So in theory, it's simple. You pick up a rock, you measure how much uranium is left, you measure how much lead is formed, and since you know the rate of change, you can calculate how long that clock has been running.
It sounds almost foolproof. It's just a ratio. Lots of lead, not much uranium, must be an old rock. So why does Dr. Mason say this is so flawed?
Because the math only works in a perfect theoretical world. He uses this great analogy that really exposes the problem. He calls it the graduated cylinder.
Right, from high school chem lab, the tall glass tube for measuring liquids.
Okay, picture that cylinder, and there's a faucet just above it, dripping water in. You walk into the room, you look at the cylinder, and the water is at exactly 300 milliliters. Right. You pull out a stopwatch, you measure the drip rate, and you find it's flowing at a neat 50 milliliters per hour.
Easy math. 300 divided by 50 is 6. The tap's been running for 6 hours. Case closed.
Is it, though? That entire calculation depends on you knowing the history of that cylinder before you walked in. For instance, assumption number 1 was the cylinder empty when the drip started.
Ah, I see where this is going. If someone had already put, say, 250 milliliters of water in it before turning on the tap, my calculation is way off. It's only been dripping for 1 hour, not 6.
Precisely. Or what about the flow rate? You measured it at 50 milliliters an hour now.
Mm-hmm.
What if 3 hours ago, the water pressure was way higher and it was just gushing out?
Or someone walked by and splashed some water in, or, I don't know, scooped some out.
You just weren't there to see it. And that is the absolute crux of Mason's argument. Radiometric dating isn't just measuring, it's measuring plus assuming. And he identifies 3 huge assumptions that map directly to those water scenarios.
Let's break those down, because this is where the fact of the Earth's age starts to feel a lot less like a fact. So, assumption number 1, initial conditions.
This is your was the cylinder empty question. The standard method has to assume that when a rock forms, like when lava cools and hardens, it has 0 of the daughter element in it. The clock is at absolute 0.
So if you're using, say, the potassium-argon method, you have to assume there was 0 argon in that rock the second it became solid.
Correct. But here's the problem. Argon is a gas. It's all over the place in the Earth's crust and atmosphere. What if some of that argon gas was trapped inside the rock as it cooled?
Or what if the magma itself was just a mix of older melted rocks that already had daughter elements in them?
Then the rock has a head start. It's like your cylinder starting with 250 milliliters of water in it. You measure it today and think, wow, this has been running for millions of years,
Right.
when actually it was just born with the appearance of age.
It's a big unknown. Okay, assumption number 2, the closed system.
This is the idea that for, say, a billion years, nothing has gotten into that rock and nothing has gotten out. It's been a perfectly sealed container.
Which just feels like a massive stretch. I mean, these rocks aren't in some sterile lab. They're underground. There's groundwater, heat, pressure, chemical reactions.
Water is the big one. Yeah. It's a universal solvent. It can literally leach uranium out of a rock or it can carry away some of the lead. If you lose some of your parent element over a million years of rainfall, your ratio is skewed.
It makes the rock look older than it is.
Much older.
Yeah.
So we don't know if the cylinder was empty and we don't know if anyone tampered with the water level. But assumption 3, that feels like the strongest one. Constant decay rates, the half-life, surely that's just physics, right?
Yeah, I thought that was like a law of the universe, a universal constant.
It has been the dogma for a very long time that a uranium atom decays at the same speed today as it did a billion years ago.
Yeah.
But Mason's sources point to some really fascinating recent research that challenges this.
This is the thing about the sun, right?
Yes. Researchers have actually observed decay rates for elements like silicon-32 and radium-226, and they fluctuate. They actually change. And they change in a yearly cycle that matches the Earth's orbit, our distance from the sun.
Wait, hold on. The sun is affecting nuclear decay here on Earth.
It seems like solar neutrinos might be interacting with the process. Now, it's a small effect in those specific measurements, but it blows the whole door open on the question. If the sun was different in the past, could the atomic clock have ticked at a different speed?
So if that clock ran really, really fast during some kind of catastrophic event, you could get millions of years worth of radioactive decay in a really short amount of time.
And suddenly your 6 hours of water flow could happen in just a few minutes.
Okay, so the whole stool has 3 pretty shaky legs. But I'm a skeptic. I can hear people listening and thinking, okay, that's all theory. Show me the proof. Because if the method is this flawed, it should fail when you test it on something real.
And it does. This is what Mason calls the reality check.
Mm.
The best way to test a clock is to time something where you already know how long it took.
The blind taste test. He brings up a volcano, Mount Ngauruhoe in New Zealand.
Beautiful mountain. It's known to have had lava flows in 1949, 1954, and 1975. I mean, we have pictures, we have eyewitnesses. We know exactly when these rocks were born.
So these rocks are, what, 50 to 75 years old, max? If the dating method works, you should come back and say 0 or, too young to measure.
Right. So samples were sent to a very respected commercial lab for potassium-argon dating. And crucially, they didn't tell the lab where the rocks came from. It was a blind test.
And the results?
They came back with ages ranging from less than 270,000 years all the way up to 3.5 million years.
I'm sorry, what? 3.5 million years? For a rock that was formed when my dad was in high school?
Yes. And it wasn't a fluke. They saw the same thing with Mount St. Helens here in the U.S.
The 1980 eruption. Big one.
That's the one. A new lava dome formed in 1986. So 10 years later, they took samples. The rock was 10 years old. The lab dates range from 350,000 years to 2.8 million years old.
That's not a margin of error. That is a complete failure. I mean, if my ruler was that wrong, any house I built would just collapse.
And Mason makes a really important distinction here between precision and accuracy. The labs are precise. Their machines are measuring the isotopes correctly. They'll give you a number like 2.8 million years plus or minus 5%. But the age is accurately wrong.
Because the assumptions were wrong. The rock must have started with a bunch of argon already in it.
It violated assumption number 1. And this leads to a really disturbing question. If the method is this wrong on rocks where we can check the answer, why on earth do we blindly trust it for rocks of unknown age?
Right. If it says 3.5 million when the real answer is 50, maybe when it says 4 billion, the answer is actually, well, thousands.
It definitely takes the certainty out of that 4.5 billion year number.
Now, to be fair, the scientific community, they know about this problem of excess argon. They're not totally oblivious. So they developed a fix, right? Something called isochron dating.
Yes, this is sort of the advanced technique.
So how is that supposed to fix the starting water problem?
It's clever. Instead of testing one sample, you test multiple samples from the same rock body. And you also measure what's called a sister isotope, a version of the element that's stable and doesn't change. By plotting all these ratios on a graph, the math is supposed to cancel out whatever the initial conditions were.
So it solves for X, basically. It removes the unknown variable.
It's supposed to.
Yeah.
But remember Mentengaraho, the 50-year-old
Uh-huh.
volcano?
Yeah.
Well, researchers applied this foolproof isochron method to those same rocks. The result: one calculation gave an age of 133 million years. Another gave an age of 3.9 billion years.
Billion. With a B. That's almost the supposed age of the Earth itself, for
Oh.
fresh lava.
So even the mathematical safety net just completely failed.
This gets into what Mason calls discordance. It's when you use different methods on the same rock and get wildly different answers.
Right. There's an example from the Grand Canyon where they dated the same basalt rock using two different methods, rubidium-strontium and lead-lead. You'd expect them to agree.
If they're measuring the same event, the clocks should read the same time.
But they didn't. They were off by hundreds of millions of years.
So one clock says noon, the other says it's midnight. Which one do you believe?
Well, the common practice is to believe the one that best fits the pre-existing story of the geological column. The others are just dismissed as contaminated.
Which is just confirmation bias. Okay, I want to switch gears to something I think confuses a lot of people. Carbon-14.
Yes, this is a really important distinction to make. Carbon-14 is not used for dating rocks at all. It's only for organic material things that were once alive. Wood, bones, shells, that kind of thing.
And it has a much, much shorter shelf life, right?
Much shorter. Its half-life is only around 5,700 years. The practical detection limit is somewhere around 90,000 years. After that, there shouldn't be a single atom of it left.
So if a dinosaur bone is 65 million years old, it should be completely radiocarbon dead. Zero C14.
Absolutely zero. And yet, Mason's sources point to tests done on coal. Coal is supposed to be ancient, right, from the Carboniferous period, 300 million years ago.
So definitely no C14.
They tested multiple samples from layers that were supposedly between 37 million and 318 million years old.
Yeah.
Every single one of them contained measurable carbon-14.
That it shouldn't be possible.
It gets even stranger. They tested diamonds. Diamonds are the hardest known substance. They form super deep in the earth. They're basically impervious to contamination, and they're supposed to be 1 to 3 billion years old.
A billion.
And yet, when they're crushed and tested, diamonds contain carbon-14.
So you have a billion-year-old diamond that's holding an isotope that can't possibly survive for more than 100,000 years.
Mason argues this is smoking gun evidence. The very presence of C14 proves these things can't be billions or even millions of years old. They have to be young.
Okay, but let me play devil's advocate. The carbon-14 dates on those diamonds, they didn't come back as 6,000 years, did they? The source said they gave ages around 50,000 radiocarbon years. That's still a lot older than the timeline Mason supports.
Right, and this is where his model gets really interesting. He connects it to the Genesis flood.
How does a flood change a carbon date?
Well, C14 is made in the atmosphere. The ratio of C14 to regular carbon in the air depends on things like the magnetic field and, crucially, the total amount of carbon in the whole system.
Okay.
Mason argues the pre-flood world had vastly more vegetation, huge forests that were then buried, becoming all that coal and oil. That's a massive carbon sink. Then, during the flood, massive volcanism would have released tons of old carbon CO2 with no C14 in it from deep within the earth.
So it dilutes the atmosphere. The ratio of C14 to normal carbon would plummet.
Exactly. So if you were a plant or animal living back then, you would have absorbed far less C14 to begin with.
I see. So when we dig it up today, it looks old because it has very little C14, but not because it decayed for 50,000 years. It's because it started with a really low amount.
It's like the tank was almost empty to begin with.
Uh-huh.
And when you adjust for that different atmospheric ratio, those 50,000 radiocarbon years,
It compressed down.
they compress right down to about 4,500 years, which lines up perfectly with a post-flood timeline.
That is a lot to think about. But there's one final piece of evidence you mentioned that I think is maybe the most compelling. It involves helium.
The helium leak.
Huh.
This is my favorite part.
Yeah.
Because you have two different physical clocks in the exact same rock telling two completely different stories.
Set the scene for us. We're looking at zircon crystals.
Tiny zircon crystals from a deep borehole in New Mexico. These little crystals contain uranium. As that uranium decays to lead, it fires off what are called alpha particles.
And an alpha particle is just a helium nucleus.
That's right. So as the rock gets older, it should be filling up with helium. But here's the catch. Helium is an incredibly tiny, slippery atom. It wants to escape. It diffuses or leaks out of crystals really, really fast.
It's like trying to keep air in a cheap balloon.
Exactly.
Yeah.
You leave a helium balloon for a week, it's on the floor. Now imagine leaving it for 1.5 billion years.
There would be nothing left inside. It would be completely empty.
You would think so. Researchers pulled up these zircons. Based on the uranium to lead ratio, they calculated the rock was 1.5 billion years old.
Yeah.
But then they measured how much helium was still trapped inside. The crystals still had up to 58% of the helium that had ever been produced in them.
58%. After 1.5 billion years. That sounds impossible.
According to the known laws of physics, it is impossible. If the rock were that old, the helium should have been long gone.
So you have a direct conflict. The uranium-lead clock says, I'm ancient, but the helium clock says, I basically just got here.
They actually commissioned an independent lab to measure the real-world leakage rate of helium from these exact zircons at various temperatures. They got the hard data.
And where did the data point?
If you assume the rock is 1.5 billion years old, the data makes zero sense. The leak rate is way, way too fast. But if you flip it around and use the measured leak rate to calculate the age,
How old is the rock?
the calculation comes out to 6,000 years, give or take 2,000.
Wow. So the physical diffusion clock points directly to a young Earth. But then how do you explain all the lead? If it's only 6,000 years old, why does it look like billions of years of decay happened?
And that brings us right back to the beginning, the idea of accelerated decay. Mason proposes that during a past catastrophic event, nuclear decay rates sped up, maybe by a factor of 1 billion.
So it generated all that lead really quickly, and it generated all the helium really quickly.
Exactly. But because it happened recently, the helium just hasn't had enough time to leak out yet. It's a single coherent model that explains both the old lead data and the young helium data. The standard model has no explanation for the helium. It's just an anomaly they ignore.
It really makes you stop and think. We started this deep dive with this idea that the age of the Earth is just settled science.
And what we found is that it's a science built on a story about the past being slow and gradual, just like the present. If you assume that story is true, you get billions of years. But if you actually look at the data that doesn't fit, the young lava dating is old, the carbon-14 in diamonds, the helium still trapped in the rock, that data seems to be screaming a very different story.
A story about a young Earth and a major catastrophe. It's that phrase I keep coming back to from Mason's work. Precisely wrong. You can measure the atoms down to the decimal point, but if your starting assumptions are wrong, you'll never get the right answer.
It changes how you look in a canyon, a mountain, everything.
So here's the final thought for you to chew on today. We often look at a landscape, like the Grand Canyon, and we're told we're seeing deep time. We feel small against those millions of years. But what if that history isn't deep? What if it's just violent? What if we're looking at the aftermath of a catastrophe that happened not in some misty, unimaginable eon, but within the span of human history?
It certainly makes the rocks feel a little less set in stone.
Thanks for diving deep with us. We'll see you on the next one.